Hello, 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 hello. Hello, 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 hello. We are live. It's been a few days and we are here. We are here, we're live. Welcome, everybody. Welcome, my continents. Welcome, Africa. Welcome, Asia. Welcome, Europe. Welcome, North America. Welcome, South America. Sorry, I've caught a cheese in my mouth. I was just eating that a little bit ago. But welcome, Australia, New Zealand, Antarctica, all my continents, everybody, Europe, Asia, Africa. Hopefully, I said all of the continents. And welcome so much to this live where we will be talking about large scale structure. So, last time when we went live, we had a pretty interesting conversation and we actually talked about certain questions that I will be covering which has to do with which have to do with particle physics and sort of the progression of particle physics and how that plays a role in everything. But today I have this book with me called Cosmology: A Short Introduction by Peter Coles, and we will actually cover something from this book because this book is extremely overdue. Back to the Boston Public Library. Thank you so much to the library for letting me borrow these books and often for forgiving me when I am way past these deadlines. So tomorrow I have to go return this. So for sure, we should take advantage of the topic on large scale structure while I have the book with me. So that's what we'll talk about tonight. But indeed, I have still in my notes some of the other topics written down that people were requesting last time. So thank you so much, everybody, for being here. Hopefully, you're joining. Hopefully, many of you, I will see you on the live very soon. Many of the old friends that usually come to the live, welcome so much and thank you, and hope to see you, as well as new friends. If you're new to the live, this is the sort of channel and live stream where we talk about physics. We actually present kitty cats physics. So it's a cats plus physics channel. Indeed, it is a cats plus physics channel. It's a catfluencer physics tuber kind of channel. And the physics topics specifically that we cover are cosmology, astrophysics, particle physics, astronomy, cosmology, those types of things. And so today, what we will cover is cosmology, which is, of course, the study of the cosmos, study of the universe at a large scale. And a very relevant topic inside of that is the large scale structure topic and how structure formed at a large scale. Hello. Hello, Domenico, says ciao to Bella. Hello, Domenico. Himothy says, do you support queer and trans people? Well, of course, yes. You should check out my TikTok called Boston Girl, where I am actually covering the Boston Pride. Um, yes, so I'm in Boston, by the way, and we just had an amazing Pride parade and Pride celebration this past weekend, and I've been kind of a little bit busy actually covering that. So I cover more content sort of associated with Boston, the city, and events in Boston, and that's totally fine. I will, for you, since you ask, I will post something on here as well. So please do like, share, and subscribe. Please like and subscribe, everybody. If you want to stay tuned to all of our updates and the physics and the cats and the pride and Boston and everything, please do like, share, subscribe, and please hit the like button or the double tap of the screen, please, to give us some likes. So, do you support queer and trans people? Asked Timothy. Of course, my love. Onyx says, I wish I can go to outer space. You know, outer space could have a few challenges. We can talk about that. Timothy says, I. Prodgen says, hi. Hello, Prodgen. Girl, I don't got TikTok. That's why I'm on here. Hello, Timothy. That's totally okay. We've got you covered here. Happy Pride Month, says Prodgen or Prodgen. Happy Pride Month indeed. Happy Pride, happy Pride, happy Pride, everybody. Thank you so much. Onyx says instructions on how to go to space. That's true. We can definitely cover that. JB says hi. Hello, JB. Harry Baker says happy Veterans Month. Happy Veterans Month. Progen says, how are you? I'm good. I'm all right. So yeah, just a side note, this past weekend was the Boston Pride, and I was sort of a journalist for that, if you will. And I was there, and I covered the whole the almost the whole parade because I was basically hopping from group to group to group, going to each part of the parade, and I just couldn't stop taking photos and videos. So actually, my phone is now malfunctioning because of all these videos and photos that I have on the device that is kind of exceeding its storage limits and whatnot. So I am having no choice but to post a lot of it on the various platforms that I'm part of and where I have sort of an account or a following or whatever. And TikTok is one of them. YouTube is one of them. On YouTube, I am mostly focused on cats and physics. But on my Instagram, TikTok, and other platforms, I've got some other content as well, which is more specific to Boston and travel and lifestyle and things like that. But right now, of course, this month, one of the biggest events in Boston was, of course, the Pride event, which went really, really well. So if you are interested in those pictures and videos, I will definitely make sure to post some of that here as well. So thank you so much for reminding me. Projin says, that's what says happy, well, happy straight month. Well, that's like every month. I think we should definitely take into account and shout out for Happy Pride Month this month. Onyx says some jokes, please. I will sub. Okay. I don't know if we will be able to give you too many jokes. I think the only jokes I say are the ones that are like part of, actual reality. People laugh sometimes, but I'm not trying to be funny. Have you ever seen a fur? Um, it's a hobby. I don't know. I don't know. I don't know what that is. I don't know what that word is. So, by the way, I should share the live really soon here, but let me get back on the topic of today, which is, of course, I always say hi to everybody and like to touch base with everybody that's joining because it gives me a feel for who is here and what sorts of interests and what kind of new audiences are joining my channel. Please do like, share, subscribe. Please do subscribe and stay tuned to these types of content that we are posting. But definitely, we will keep our focus on the physics topic of today. Soon, I will start talking about that. We will be using this book by Peter Coles, and I'm going to get back to your comments a little bit later once I have covered some of that topic, and I will touch base again with all the comments and everybody who is posting in the chat. Okay. So thank you once again for being here. Let me share the live while I'm at it. Can everybody see me, hear me okay? Hello, Random Man. Hello, Progen. Hello, Onyx. Hello, That's What. Thank you for commenting and for being in the chat. So, we have covered quite a few different physics topics on the channel. There was a time when we were covering a lot of astronomy. It was mostly all astronomy, astronomy, lots of astrophysics as well. And we actually have an entire playlist on just planets. So if you're new, by the way, if you're seeing this video later on, if you're new, we have a lot of content that you should definitely check out, both under the live tab as well as the videos and the shorts and things like that. So we post pretty much in every format. There's the live streams that get posted under the live tab. Then there's the videos, the clips, and then also shorts. And also I post under post tab. So let's see. Let me share the live really quickly before we get on business here. I opened up my channel and I got distracted because I was like, I don't know what I'm doing actually. I meant to share the live. That's what I'm doing. So hang in there 1 second. We are live. Let me tell my channel that we're live. How's everybody doing? Sometimes there's quite a bit of drama in this classroom. So if you're new, I'll just kind of warn you about that. Hello, Random Man. You might want to tone it down because if one of my mods join, then you'll probably get banned, my friend. I'm in a very zen mood because I went to the gym and I did my swimming and pretty much I'm extremely zen and feeling very happy with the thanks to the universe, with the thanks to God, and none of the comments here can really get me out of character, but I'm just warning you for your own sake that indeed you may have to suffer the wrath of some moderators that we have on here. They might have gone to bed. In that case, carry on being weird, and YouTube will probably censor some of the words that you're saying. So, okay. Could you please double tap the screen and give us some likes? That would be great as well. Looking at the live on my live monitor to make sure that it's all set up correctly. Okay. Ah, there. Hopefully the sound is good. I certainly hope that people can hear me. So, okay, cancel that. Okay, all right. Let me type. Please do like and sub. Hi, Projen. How are you doing? All right. So as I get started on the topic, I will take a break from reading your comments for a little while, and then I'll get back to all your comments. And so everybody, if you're putting something in the chat, then fear not. I will read every message quite soon here, and I'll give you all a shout out, your usernames and everything like that. So you look like Cleopatra. Thank you. I do like Cleopatra. Actually, I like Julius Caesar as well. I love Rome. I love the Roman Empire. And Cleopatra was quite intimately connected with the Roman Empire. So Desmond says, hello from Las Vegas. Hello, Las Vegas. How are you doing? Oh, and also, of course, I should mention in that same sentence about Rome that, of course, the Roman Empire borrowed a lot from Egypt. So, you know, of course, they were connected. So, anyways, that was my response to the Cleopatra comment. Thank you so much. Lauren, 5-star. Lauren, 5-star with the star emoji. Thank you. So, let's see. Okay. All right. So let us get going with this topic for today, which is cosmic structures. In particular, sometimes it's called large scale structures. Now, remember that in the very beginning of the universe, when the universe got started with the Big Bang, there was this hot, dense, energetic, really crazy soup of photons, electrons, and positrons, mainly very radiation dominated, is the other way of putting it. And of course, the universe was very tiny. And at some point, the expansion of the universe started. And much later, actually, these types of things like large scale structures, the galaxies, the first stars started to come to exist. And something like little perturbations to an overall otherwise smooth universe actually might have led to this large structure in the universe, which is a current topic of research. Exactly how tiny overdensities in what we generally consider a smooth universe at a at a certain general sense, it's a smooth universe, but how did certain overdensities or certain clumps of matter here and there um, ultimately lead to us getting galaxies, stars, and these types of distribution of matter, in other words. So large scale structure is more than just the scale of our galaxy, our neighboring galaxies, and their neighboring galaxies. It is really quite literally in the universe. Why is there sort of a large scale structure? What kind of determines the distribution of matter in the universe? And in the distribution of matter in the universe. And indeed, it is a topic of research to figure out what kind of influenced this distribution of matter. What types of things can influence this distribution of matter, and what are some of our thoughts on that? What are certain models, maybe? Because in cosmology, there's a lot of models which can be tested out with some data if the data comes in. But actually, you can also tune a lot of parameters in your models and just kind of test things out, like just kind of see what that does to the model of the universe in your model, that is, and then try to verify with the reality, with the incoming data as data gets collected more with experiments, as we have better technology to do experiments and to do observations. So remember, in the past, about 100 years ago, there really was not, or over 100 years ago, I would say, there really was not much of a drive to collect a lot of data at the cosmological types of scales. So we've come a long way in terms of, hello, we've come a long way in terms of being able to collect data much, much better now. So given that we have a ton of different models, we have even the Big Bang itself is a theory, it's a model. We have these ideas. Given that we have all this, we can pair that with some of the incoming experimental observations and see where that takes us in terms of our understanding of the large scale structure in this universe. So let's see what this book has to say. And keep in mind that we are considering the overall distribution of matter in the entire universe and not just the shape of a single galaxy or even a few galaxies, but really, why is the distribution of matter in this universe the way it is? Okay. So galaxies are the basic building blocks of the universe. They are not, however, the largest structures one can see. They tend not to be isolated, but like to band together, rather like people. The term used to describe the way galaxies are distributed over cosmological distances is large-scale structure. So this is what we mean. If you do research in physics, if you're in academia, or if you kind of follow these topics, you might come across this expression, large-scale structure. And that's what this means. It's the distribution of galaxies or the distribution of matter over cosmological scales. The origin of this structure is one of the hot topics of modern cosmology, but before explaining why this is so, it is first necessary to describe what the structure actually is. So somebody asked, where did matter come from? So ordinary matter, or baryons, protons and neutrons, the first little bit of matter like hydrogen and helium actually came from the Big Bang. So the Big Bang gave us hydrogen, which is merely just protons, and a little bit of helium. All of the other heavier elements actually have been made in stars, but stars come into the picture much later. We will talk about large-scale structure today, so stars are related to that, but basically, before you can have stars, this whole question of how did the galaxies even come to be? Was there any, what is causing this large scale structure? What is causing structure to form at all in the universe is what we're covering today. But yeah, to answer the question, hydrogen comes from the Big Bang. The Big Bang nucleosynthesis process gave us some hydrogen and a little bit of helium and very trace amounts of lithium. All of the other heavier elements are made in stars. When they die, they spew their material out into outer space, and that can form gas clouds and nebula, and that goes on to give us the next generation of stars and the next and the next. And the sun comes from a gigantic and very interesting and very metal rich and very abundant gas nebula in our galaxy. Okay, so we all come from a gas nebula that condensated at some point to make the sun and the planets. Okay, so patterns in space, the distribution of matters on large scales is usually determined by means of spectroscopic surveys that use Hubble's law to estimate the distances to galaxies from their redshifts. So remember, in astronomy or cosmology or astrophysics, a lot of these measurements depend on spectroscopic data and trying to understand the redshifts of these objects that are far, far away to figure out exactly how far they are and what sorts of distances are involved here, and are they being affected by the expansion of the universe or not? Okay. The existence of structure was known for many years before redshift surveys became practicable. So, by the way, this redshift data that we talk about here, collecting more data to get this data, has happened over the years. We did not have redshift data for so many galaxies and so many other objects in the sky for forever, right? This is kind of a new thing. Hi, G, pirates. So the existence of structure was known for many years before redshift surveys became practicable. The distribution of galaxies on the sky is highly non-uniform. So that's the other interesting thing, is that the distribution of matter in this universe is not a uniform distribution. So it's got there's some method to the madness as far as the distribution of matter goes. And we would like to understand how it ended up being this distribution. What are some of the factors affecting it? As can be seen in the first large systematic survey of galaxy positions, which resulted in the Lick map. So this sort of positions of galaxies in the sky has been collected as more and more observational data has come in, and we've basically got these surveys now which tell us how the distribution of matter is in the universe, and we can sort of see sort of a shape kind of forming, if you will, and this shape is telling us that it's not a uniform distribution. There is some kind of reasoning behind the distribution one would imagine, and we want to know what that reasoning is. So it's a very interesting sort of mystery, if you will. Okay, so impressive though this map undoubtedly is, one cannot be sure if the structures seen in it are real physical structures or just chance projection effects. After all, we all recognize the constellations, but these are not physical associations. The stars in them lie at very different distances from the sun. For this reason, the principal tool of cosmography has become the redshift survey. So they are, this book, another thing that I should mention, that this is not the most latest and greatest information or data either. This book is a sort of a textbook, if you will, that can give us some idea about the evolution of this topic in cosmology. It might not be the exact latest and greatest from like yesterday, but the truth is that they were trying to figure out this distribution of matter in the universe, and that is not an easy thing to do. As more technology progresses and we can collect more and more data, first of all, we have to have more than one data point, right? So all of these objects in the sky, hopefully galaxies, understanding exactly how far away they are, that's how we will map them, right? If we don't know where they are, then we don't have a map of them. Once we have a map of them, once we have enough data coming in, we can sort of try to understand, okay, well, what is the shape of this distribution, right? But without a lot of data, that's kind of impossible. And without sort of settling on a way in which we can say exactly where they are is another sort of thing. And ultimately, it seems like these people kind of settled on the redshift types of surveys, okay? A famous example of this approach is the Harvard-Smithsonian Center for Astrophysics survey, which published its first results in 1986. So this was quite a while ago, so it's good. We are kind of going down memory lane. If you're from that time, then it might be familiar to you if this happened. But if you're, sort of newer than this survey, then we can look back at the past here. This was a survey of the redshifts of 1,061 galaxies found in a narrow strip on the sky in the original Palomar Sky survey published in 1961. So these types of surveys have been happening for a while. So it's good. If you're doing a survey now, it's not like you have to start from scratch. you can go back and see what was covered in previous surveys of the sky and sort of add to it, if you will. Maybe update it. Maybe you find something new, or find that something was wrong and you update it. And it's a work in progress. So don't ever consider these surveys to be totally done. Okay. This survey has subsequently been extended to several more strips by the same team. Until the 1990s, redshift surveys were slow and laborious because it was necessary to point a telescope at each galaxy in turn, take a spectrum, calculate the redshift, and then move to the next galaxy. So literally they're taking the spectroscopic data from the galaxy objects. Basically, these are sort of dots in the sky with our naked eye, right? I mean, if it's even visible to the naked eye. So by the way, when you look up at the sky, I do believe that most of the things you see, that most of the dots or the stars in the sky are actually galaxies. And so pointing a telescope at each of these galaxies, collecting the spectroscopic data, collecting the data, basically taking in all of that light to figure out how far away they are. It's not a joke. It's sort of quite a lot of work. And it used to be quite laborious, as they're saying, because you had to really take each galaxy in turn and point the telescope at that one by one. So to acquire several thousands of redshifts took months of telescopic time, which, because of the competition for resources, would usually be spread over several years. So another thing is that it's called getting telescope time. Just because you are interested in an object doesn't mean that people will give you unlimited telescope time to look at that object. It can happen that there is some other deemed to be higher priority object by some other group or something, or funding or something, that requires telescope time, and there's only so many telescopes. It's a limited resource. So the other thing is that you might not get unlimited telescope time, even if you really like an object, and even if you really wanted to look at it for forever. Telescope might be needed somewhere else. Okay, so that's another thing too. So to acquire several thousands of redshifts took months of telescope time, which, because of the competition for resources, but meaning telescope resources, would usually be spread over several years. More recently, the invention of multi-fiber devices on wide-field telescopes has allowed astronomers to capture as many as 400 spectra in one pointing of the telescope. So this is where we've talked about how the 21st century is really more about fine-tuning and making our instruments better and making technology better in order to be able to do better experiments and better observations. And this is very much a part of it, is that remember how this idea for looking at galaxies and trying to collect the data to do this work was already there for decades. But to get to the technology where we can do it better and more efficiently is something that we are now talking about, okay, that where we have been needing to get better at. So among the latest generation of redshift surveys is one called the 2-degree field, or 2DF survey, run by the United Kingdom and Australia using the Anglo-Australian telescope. So welcome, Australia, welcome the UK. If you're here, we're talking about your telescope now. Hello, everybody. This will eventually map the positions of around 250,000 galaxies. How nice, how nice. And somebody, by the way, you can look up the 2-degree field survey. This book is pretty old, so it should have been coming out with its data already. So you can look this up if you like, probably on Google. The general term used to describe a physical aggregation of many galaxies is a cluster of galaxies, or a galaxy cluster. So you might have heard of that as well. Clusters can be systems of greatly varying size and richness. For example, our galaxy, the Milky Way, is a member of the so-called local group of galaxies. So we have a local group of, or a local neighborhood of galaxies around us to which we belong, and it is called literally local group. So which is a rather small cluster of galaxies, of which the only other large member is the Andromeda galaxy, or M31. So by the way, we talked about how Milky Way Andromeda merger is not such a sure shot certainty. At this point, there's a 50-50 chance that maybe we will merge with Andromeda in the next 5 or 10 billion years, or maybe we will not. It's a 50-50 chance. We talked about that in one of the recent live streams. If you're interested, by the way, it was a lot of fun. At the other extreme, there are the so-called rich clusters of galaxies, also known as Abel clusters. Abel ABELL, Abel or Abel, I don't know exactly how to say it, but it's ABELL, Abel clusters, which contain many hundreds or even thousands of galaxies in a region just a few million light years across. So there are other parts, but this is an example of sort of the non-homogeneity, where we belong to a cluster which doesn't have too much going on. The only other big one that we know as far as galaxies in our neighborhood is, of course, the Andromeda, beautiful Andromeda galaxy. But there's other extreme parts of this universe, such as this Abel cluster, which is a very rich cluster of galaxies because there's many hundreds or even thousands of galaxies in a region just a few million light years across. A few million light years across may seem like a lot, but it's really not that bad. Just our galaxy across is 100,000 light years. 100,000 light years across is just our galaxy. So a few million light years across, that is the time light takes to go from one end to the other. A few million light years across is not that big, right? So having lots of galaxies in that space is quite a lot. Prominent nearby examples of such entities are the Virgo and Coma clusters. So you might have heard about the Virgo cluster. I believe the Virgo sun sign, the zodiac sign, is named after that cluster, if I'm not mistaken. And Coma clusters. So I believe the Coma cluster, COMA, literally looks like a comma. So in between these two extremes, galaxies appear to be distributed in systems of varying density in a roughly fractal or hierarchical manner. The densest Abell clusters are clearly collapsed objects held together in equilibrium by their own self-gravity. So, one second, something in my eye. The less rich and more spatially extended systems may not be bound in this way, but may simply reflect a general statistical tendency of galaxies to clump together. Individual galaxy clusters are still not the largest structures to be seen. The distribution of galaxies on scales larger than around 30 million light years also reveals a wealth of complexity. Recent observational surveys have shown that galaxies are not simply distributed in quasi-spherical blobs. So they're not always in these quasi-spherical blobs like the Abell clusters, but also sometimes lie in an extended quasi-linear structures called filaments. So sometimes the structure or the large-scale structure in the universe looks kind of like a filament. It doesn't always have to be sort of a blob or a spherical-looking thing. It can be sort of a filament, okay? So interesting things in very interesting shapes indeed. Not always something that you might intuitively think of. So, or flattened, sometimes even flattened sheet-like structures such as the Great Wall. This is a roughly two-dimensional concentration of galaxies discovered in 1988 by astronomers from the Harvard Smithsonian Center for Astrophysics. The Great Wall, so literally it's called the Great Wall, like the Great Wall of China, but in this case, Great Wall in the universe, is at least 200 million light years by 600 million light years in size. So 200 million light years by 600 million light years in size, in a 2D way, if you will, but it's less than 20 million years thick. So not very thick, but pretty long, pretty wide, but not very thick. So more like a filament. It contains, or more like a sheet, sorry. It contains many thousands of galaxies and has a mass of at least 10 to the 16 solar masses. It contains many thousands of galaxies and has a mass of at least 10 to the 16 solar masses, 10 to the 16, 10 to the power 16, 1/6 solar masses. The rich clusters themselves are clustered into enormous, loosely bound agglomerations, that's quite a word, agglomerations, called superclusters. Many are known, containing anything from around 10 rich clusters to more than 50. The most prominent known supercluster is called the Shapley concentration, while the nearest is the local supercluster. Centered on the Virgo cluster mentioned above, a flattened structure in the plane of which the local group is moving. Interesting. Superclusters are known with sizes as large as 300 million light years, containing as much as 10 to the 17 solar masses of material. These structures are complemented by vast, nearly empty regions. Remember, lots of empty regions too in outer space, many of which appear to be roughly spherical. These voids contain very many fewer galaxies than average, or even no galaxies at all. Maybe even no galaxies. Okay? So lots of voids as well. And I'll show you, by the way, the 2DF Galaxy Redshift survey. If you haven't seen it already online somewhere, I will show you the survey here in a bit. Voids with density less than 10% of the average density on scales of up to 200 million light years have been detected in large-scale redshift surveys. The existence of large voids is not surprising, given the existence of clusters of galaxies and superclusters on very large scales, because it is necessary to create regions of less than average density for there to be regions of greater than average density. So, of course, there's going to be some voids. The impression one has when looking at maps of large-scale structure is that of a vast cosmic web. So this cosmic web-looking thing, you will see it in this picture. You might be familiar already if you've looked at galaxy survey type of images. A complex network of intersecting chains and sheets. So there's the blobs, there's the sheets, and then there's the chains. And sort of this complex network of a web of them. But how did this complexity arise? So remember, the primary question here is, how do we have this large scale structure? How do we have this large scale shape, if you will, the shape of the distribution of the matter in the universe at a large scale, quite literally a large scale, cosmic scales, universe scales, not just the scale for little of our neighboring galaxies, but at a large scale. What is the reason for this distribution? That's the question. The Big Bang model is predicated on the assumption that the universe is smooth and featureless. So at a sort of a less specific level, the universe is considered to be very smooth, as in hardly any clumping. So it's considered to be smooth and featureless. But actually, if you look more deeply, more specifically, there exist these higher order, we call them higher order perturbations to the smooth universe, these regions of overdensities, actually, overdensities. Now, I mean, think about it. If there were no overdensities, if there was not a little bit of gravitation winning against expansion, then we would not have galaxies and we would not have stars and we would not be here, right? So there's these little clumping, if you will, of matter, which is the overdensities, which was this sort of higher order correction to the smooth universe. But the question is why? Why were these overdensities? What is the cause of the overdensities? So that is the topic here. That is the research question, okay? So I'm not sure that this has been answered, but this is what we're talking about, okay? So the Big Bang model is predicated on the assumption that the universe is smooth and featureless. So if you are not interested in a lot of details and you just want an approximation of the universe and it is considered to be smooth and featureless, that it conforms to the cosmological principle. Fortunately, the structure does indeed seem to peter out on scales larger than the scale of the cosmic mesh. This is also confirmed by observations of the cosmic microwave background, which comes to us after traveling about 15 billion light years from the early universe. Now, the cosmic microwave background photons, as we know, are sort of from when the universe itself was around 300,000 years old. So very early primordial photons these things are, because 300,000 years old for the universe is still pretty early, given that the universe at this point is around 15 billion years old. So this sort of signature of the photons that we have from the early universe, which we call the cosmic microwave background radiation, if you're not familiar, we've kind of mentioned it in other lives as well, and you can look it up. Basically, it is sort of this radiation that is everywhere. No matter where you look, it's very isotropic, very isotropically distributed. Doesn't matter where you look, in what direction you point your instrument, you always pick up on the cosmic microwave background radiation. So it's always there. And it is a primordial radiation. It is from those early times of the universe. I don't want to say early days because it is, I believe, the universe was about 300,000 years old at the time of the cosmic microwave background radiation situation. But even that signature actually generally speaking, gives us a smooth universe, as in it is homogeneous. What do we mean by smooth? Homogeneous, isotropic, not very much differing, not much variation, or shape change as you look in different directions or as you move away, okay, from a certain, say, given point of where you choose to be. Basically, the cosmic microwave background radiation is another look at this, generally speaking, smooth universe. But the devil is in the detail, because even in the cosmic microwave background radiation picture, you actually do find little overdensities, which you'd have to look very carefully, and you have to study this thing for a while, and it has been studied for a while, a couple of decades at least. And there you actually see the tiny little signatures of the clumping of matter. But overall, it's considered to be smooth. But there are little tiny non-homogeneities even in that smooth universe. Again, where do these come from? We will have to figure out. But this is what is probably leading to the distribution of matter, the distribution of the large-scale structure, or the shape of the large scale. Even the fact that there is clumping, there is any kind of galaxies forming, et cetera, et cetera. Gravitation has to win at some point. Otherwise, why would you have galaxies, right? Matter getting close to each other, in other words. So this is also confirmed by the observations of the cosmic microwave background, which comes to us after traveling about 15 billion light years from the early universe. The microwave background is also a uniform on the sky, consistent with the cosmological principle, almost that is, but not quite. So this is what I was just now saying, which is that the cosmic microwave background radiation also shows us the smooth universe. It is not just our, the Big Bang theory. It's a theory. I'm not saying it's perfect. Of course, it has room for improvement. But the Big Bang theory, there are lots of experimental observations that confirm it to a large extent. The cosmic microwave background radiation is very, very important evidence supporting the Big Bang. Because, if the Big Bang is basically saying you should have this smooth universe, and the cosmic microwave background radiation to a large extent, generally speaking, is smooth, homogeneous, isotropic, then it's kind of a good confirmation of this theory, right? So it's kind of this win for the Big Bang. And the fact also that we have expansion in the universe, because remember, there's gravitation, and the anti-gravity effect in the universe is, of course, its expansion. Hello, Crazy Sick Wine, how are you doing? So the anti-gravity phenomena in the universe is expansion, dark energy. We call it dark energy because we don't quite understand why the universe is expanding. We call it cosmological constant, depending on who you are, depending on which part of the evolution of cosmology you're in. Or in other words, we call it dark energy. There's surveys now called dark energy survey, dark energy spectroscopic instrument, another type of survey. There's questions about the expansion of the universe as well, right? That too is a mystery. That too is something that we are currently researching. But the fact that we do have observational evidence for the expansion of the universe is another win for the Big Bang theory. The universe is expanding, so when you go back in time, the forward time is where expansion is happening. But if you go back in time, you go back to that singularity, which is the Big Bang, which is where we come from, according to the Big Bang theory. Now, you can believe in it or not, or you can point out its deficiencies for sure, as you should, but to a large extent, the Big Bang theory is quite successful. Okay. And so imagine as more and more pieces of evidence like the cosmic microwave background radiation come in, and not only just came in one day, it came in over decades, right? Couple of decades or more of experimentation and observation and analysis has happened for this type of data by different groups, and they see more or less a smooth universe. That's a very big win, right, for the people who might have predicted that. Now, smooth, homogeneous, uniform universe. If everything was really quite that perfect, then we would not actually have galaxies probably, because again, we would need gravitation to sometimes win locally for there to be galaxies, right? Overdensities. So what do these overdensities come from? There are tiny little higher order perturbations for the smooth universe, to the smooth universe. As in, we can call it smooth, but at a higher order, there are little overdensities in there there are actually little tiny non-homogeneities in the smooth universe, which we must take into account, which we must understand in order to understand how the structure happened. And that's what we're talking about right now. Okay. So in 1992, the Kobe satellite deployed its sensitive detectors to the task of detecting and mapping any variation in the temperature of the microwave background on the sky. So they are looking for this variation. So the cosmic microwave background radiation is giving us a temperature for the sky. In other words, right? Those photons have a temperature associated with them. So it's almost like these are some pretty old photons. These are primordial photons. These are from universe was like a baby at that point. So understanding these photons, first of all, is very useful for us to understand those early times of the universe. But also, we know that structure formed, right? We know that galaxies are a thing. So if everything was always perfect and homogeneous, then how did galaxies form? So we want to look for variations. We want to look for any little overdensities, any little variation, or basically, what's the word? Little bit of going away from the smoothness. Basically, we want a little bit of overdensity. We want a little bit out of that homogeneous, just a tiny little bit of non-homogeneity in the smooth universe. We want to find that. We want to look harder so that we can find that, because if we cannot find that, then it doesn't make sense to have galaxies. Okay? Fluctuations, yes. Ah, thank God. Somebody said it. Thank you, Skeletor. So we want to find these little fluctuations from the smooth universe, and the fluctuations can be very tiny. Thank you, Pranay. Thank you, whoever said fluctuation, Skeletor. It's like it's a smooth universe, but there's got to be tiny little fluctuations. Otherwise, how do you ever get any kind of clumping or overdensity, leading to gravitation winning finally in some spots of the universe, giving us galaxies and stars? Okay. So they're looking for this variation now. At its discovery in 1965, the microwave background seemed to be isotropic on the sky. So we know that already. We know already that the CMB is very isotropic. This is what I was talking about earlier, is that no matter what instrument you use, no matter which direction you looked at in the sky, because the Earth is pretty round, we can go to a different part of the Earth and point the telescope, point our instrument in a different part of the sky altogether, and we still picked up on the same darned CMB. It was very isotropic, very like homogeneous in all directions. Okay, didn't matter where you pointed your instrument, you still picked up on the same darned, pretty much the same CMB signature. Okay, you'd have to really look to find these fluctuations. And thank you, whoever said fluctuation. Later, it was found that it had a large scale variation across the sky of about 1 part in 1,000 of the temperature. 1 part in 1,000. So when I say that the fluctuations are tiny, I mean tiny. These are not like, fluctuation as in plus or minus half. Like the number is not like 5 plus or minus 2. The fluctuation is very small. That's why they didn't find it earlier, right? When they're looking and looking and looking and getting the CMB photons, the cosmic microwave background photons, the primordial photons, it's just the same. No matter where you look and how you look and in what direction you look, it was pretty much the same always. They had to really, really, really look for these fluctuations, these variations, because they're very small indeed. So anyways, they found that it had a large-scale variation across the sky of about 1 part in 1,000 of the temperature. This is now known to be a Doppler effect, oh good God, caused by the Earth's motion through the radiation field left over from the Big Bang. The sky looks slightly warmer in the direction we're heading and slightly cooler in the direction we're coming from. But aside from this dipole variation, as it is called, the radiation seemed to be coming equally from all directions. So even this one is a Doppler one. Gosh, good God. But theorists have suspected for a long time that there should be structure in the microwave background. In other words, there should be some kind of variation in the microwave background. It should not be totally same, homogeneous, and smooth, in the form of a ripply pattern of hot and cold splotches. So people wanted to find these hot and cold splotches. It's like Sherlock Holmes looking for what he believes should be there. Because we know that there is structure, we know galaxies formed. We are in a galaxy ourselves. So how will galaxies form if everything is always homogeneous? It was these that Kobe found that, and in doing so, caused newspaper headlines around the world. So the hot and cold splotches. So why is the microwave background not smooth after all? Now remember, it's mostly, for the most part, if you don't care about the details, it is smooth. But there are a little bit of overdensities. Why? The answer is intimately connected to the origin of large-scale structure, and as ever in cosmology, gravity provides the connection. I would freaking hope so anyways. Like I was saying, there has to be some way in which gravitation has to win. If gravitation did not ever win, the universe would expand, nothing would be clumping, no galaxies would be forming, stars would not be forming, nothing, we wouldn't be here. Because we are here because stars formed and stars died and stars made the heavier elements while alive, and then they supernovaed and they spewed their rich materials into the space, and that formed gas clouds, and then that cooled enough to make our sun, and then the planets, and that's why we're here, right? So, it all comes from the galaxies and the star formation. If gravitation is never allowed to win, we cannot be here, okay? Friedman's models provide important insights into how the bulk properties of the universe change with time, but they are unrealistic because they describe an idealized world that is perfectly smooth and blemish-free. So Friedman did pretty good job with his equations. Remember, he did a really good job for the expansion of the universe, I do believe. But of course, again, he's not going to necessarily capture every little detail about the universe. It's very impossible for somebody to one person to describe the entire universe. Friedman might have done a very good job at giving us expansion, for example, and giving us a pretty overall good description of the universe, right? The fact that there is expansion, the fact that there's the cosmic microwave background, smooth universe, because pretty much it is smooth. So Friedman did a good job, and we've talked about, by the way, there was a live called Friedman Equations earlier that we talked about, and other lives too, where we cover all this. But of course, he cannot capture every little thing in his equations, and by little I mean really little, with these overdensities, which must have led to large-scale structure. And if anybody knows anything about that, feel free to put it in the chat as well. But they are unrealistic. Friedman equations unrealistic because they described an idealized world that is perfectly smooth and blemish-free, but at least he did a good job with the expansion, you know. It's fine. It's fine. If somebody comes up with equations for the smooth universe, they're probably doing a very good job to explain the expansion of the universe, which is also a very important topic indeed, okay? We talk a lot about the expansion of the universe. Dark energy, that's a huge topic, right? It's just the unfortunate thing is that expansion is not going to tell you why there are galaxies, right? Right? It's just common sense. So a universe that starts out like that will remain perfect forever, okay? So according to Friedman, he believed in perfection, and he also just kind of worked on that. You know, it's fine. It's fine. One person cannot work on everything. In a realistic situation, however, there are always imperfections. Some regions may be slightly denser than average. Some are more rarefied. How does a slightly lumpy universe behave? Slightly lumpy, clumpy, forming galaxies, forming the stars. Later on, first the galaxies, right? Slightly clumpy, slightly lumpy, slightly variation, slight fluctuations. Slight fluctuations. How does that behave? Because Friedman didn't tell us how that one behaves, okay? The answer is dramatically different to the idealized case. A piece of the universe that is denser than average exerts a stronger gravitational pull on its surroundings than average. Of course, thank gosh. Thank gosh for gravitation, right? Thank gosh for gravitation, because if gravitation, like I said, never won, we would not be here. So in some parts of the universe, you do have to let gravitation win. Otherwise, we would not get galaxies, right? It will therefore tend to suck material in, depleting its neighborhood. Depleting its neighborhood, because remember, if some spots have more matter, other spots have to have less matter. It still doesn't make total sense, as in we don't fully understand exactly why the matter distribution is shaped the way it is. As far as I know, we still don't fully understand large scale structures. So what I mean by that is we still don't fully understand the shape of the distribution of the matter in the universe. But if you don't have some matter more in some parts, then of course that means that other parts have less matter. So of course gravitation is winning in some of those parts that have more matter. In the process, it gets even denser relative to the average and pulls still harder. The effect is a runaway growth of lumpiness called the gravitational instability. Oh, how nice. Oh, how wonderful. I love it. Effect is a runaway growth of lumpiness called gravitational instability. Eventually, strongly bound lumps form and begin to collect into filaments and sheets resembling those seen in maps of cosmic structures. So, of course, this sort of lumpiness, clumpiness, thingy thing happened, but there's still some questions about exactly why the shape it is, why it is. There's still some questions, but we understand that this is probably some kind of lumpiness, clumpiness definitely happened with this gravitational instability forming. A little bit of overdensity can cause this runaway effect of the clumpiness happening more and more as its gravitational field gets stronger. But exactly what cocktail of gravitational, oh, there's Baji, gravitation type of things, and this is where we might get into dark matter a little bit later on, we will see in the chapter. Exactly what cocktail will give you this effect is something that we're still researching, as far as I know, okay? Eventually, strongly bound lumps form and begin to collect into filaments and sheets resembling those seen in maps of cosmic structure. Only very slight fluctuations are needed to kick the process off, but gravity acts like a powerful amplifier, transforming minute initial ripples into huge fluctuations in density. Wow. So that's the thing. Only very tiny little fluctuations or variations are needed to kick this process off. But as soon as you kick this process off, as soon as you allow for a little bit of overdensity, overdensity meaning that fluctuation in the smooth universe, overdensity meaning that variation in the smooth universe, a little bit is needed, and then gravitation will take off. Gravitation will do its thing. Strong gravitational field sucking matter in, bringing in more and more matter towards that clump, towards the lump. The more lumping happening, more clumping happening, okay? So this is the nice thing about gravitation. As soon as you give it a little hand, give it a little help, it will start to make galaxies in this universe. Now, as far as I understand, exactly like I was saying, what cocktail of matter, including or not including, I think including dark matter, plays a role in this clumpiness, lumpiness is something of a question that we're still exploring in science. But nevertheless, indeed, this kind of lumpiness, clumpiness had to have happened for us to get the galaxies, okay? So I think this is incredibly exciting that only very slight fluctuations are needed to kick this process off. I think that is just incredible to think about. We can map the end product using galaxy surveys. Now, thank goodness, we have made a lot of observations, so we know certain distributions of galaxies. And so it's not like we're totally blind. At this point, we do see sort of some distribution of the galaxies, so we can kind of see the map. And we see the initial input in the Kobe map. We even have a good, so the initial input in the Kobe map, as in the smooth universe. So The smooth universe is from a while ago, right? That is kind of like the history. That is the past. That is the past. The cosmic microwave background radiation, the smooth universe, the map, the Kobe map, the CMB map gives us that initial map. And there must have been tiny little variations in that initial map to then later give us. It's kind of like going from here to here, where the here is the Kobe map and here is the galaxy survey map. So it's kind of like now we have to put those dots, we have to connect those dots, right? We have to connect the dots of how did we get from the Kobe map, giving us the cosmic microwave background radiation map, which was smooth, homogeneous, isotropic. How do we go from there to the galaxy survey map, where we have surveys giving us map of galaxies and distribution of galaxies? How do we go from here to the there? Okay, it's kind of like this understanding of that evolution. So interesting, so very, oh, this is the loveliest topic. So very interesting. So now, so we have a way to look back in time before the galaxies formed to see, well, what was the input? And that is the Kobe map. That is the CMB radiation map, right? And that's simplemente amazing. Simplemente amazing. The basic picture of how structure forms has been around for many years. Oh, okay. The basic picture of how structure forms has been around for many years, but it is hard to turn this into detailed predictive calculations because of the complicated behavior of gravity. So even though we sort of, kind of, sort of have the input and the output, input being the Kobe map, input being the CMB map, input being the smooth universe with tiny, 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 tiny little variations or fluctuations. We hope, anyways. Otherwise, how would we get galaxies? That's the input, and then we have the output for the in terms of the galaxy survey, in form of the galaxy survey. So even though, so this is how difficult cosmology is. This is how difficult astronomy is. Even though you might have the input and the output, it's still very complicated. It's still very, 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 very complicated because you're dealing with large scale structure, all of the matter in the universe distributing and its distribution. So exactly how gravity will behave, like you need a really good model and you need to account for hopefully all the important things in order to give sort of get the reasoning, right? So even if you had the input and the output, doesn't mean that necessarily predictive calculations are easy to do because of the complicated behavior of gravitation. I mentioned in chapter 3, so this book, Peter Coles is the author. He mentioned in chapter 3 that even Newton's laws of motion are difficult to solve without simplifying symmetry. In the late stages of gravitational instability, as in where the clump becomes crazy and attracts even more things towards it, there is no such simplification. Everything in the universe pulls on everything else. It is necessary to keep track of all the forces acting everywhere and on everything. And as you can imagine, that gets to be very complicated. That's a lot. That's a lot, a lot, a lot. Lot, a lot, a lot. The sums involved are just too hard to be solved with pencil and paper. During the 1980s, however, massive computers came on the scene and progress in the field accelerated. Thank gosh. Thank you, Crazy Sick One. Thank you, Eversor. Thank you, everybody. It became obvious that gravity could form cosmic structure, but in order for it to do the job effectively, there would have to be quite a lot of mass in the universe, quite a lot of mass, quite a lot of mass, quite a lot of mass. This is where I believe dark matter might come in. We will see. um, actually, nothing is Nothing is made of a lot of things. Have you heard of particle antiparticle pairs? Look that up. And hopefully that will convince you that nothing is in fact quite a busy something. Nothing is made of a lot of things. So thank gosh, computers came to be in the 1980s, because without that, I mean, this math was just getting out of hand, completely out of hand. This math was just going above our heads. But then in the 1980s, I love that you love physics. Thank you. Can someone do a super chat, please? Can we do that? Can we do that? Can you do a super chat? Rids, I think if you do a super chat of $500, that will make you really happy. And we will prove everything immediately after. Thank you so much. So it became obvious. It became obvious. It became obvious. People were starting to sort of see that this cosmic structure may have something more going on with it, something a little bit more. Extra spices were needed to make this cosmic structure happen. Okay, so it became obvious that gravity could form cosmic structure, but in order for it to do the job effectively, there would have to be quite a lot of mass in the universe, quite a lot of mass. Are we ready? Are we ready for that? Because only a relatively small amount of normal matter is allowed by primordial nucleosynthesis arguments, theorists assumed the universe to be dominated by some sort of exotic dark matter that does not involve itself in nuclear reactions, because we actually have a pretty good idea of how much matter we got from the Big Bang. It's called Big Bang nucleosynthesis, and we have evidence to support that. So I said a while ago, towards the beginning of the live, that the heavier elements, as in heavier than hydrogen and helium, come from stars. At this point in the smooth universe, there's no stars, right? Galaxies have not formed. We're talking at that point, what is there in the universe? Hydrogen, bit of helium, trace amounts of lithium. So ordinary matter was pretty skimpy at that point, right? Even now, again, class, the most abundant element in the universe is still hydrogen. Why? Because the Big Bang gave us mainly just hydrogen. It's not like the Big Bang gave us a lot more than that. We had to make that with stars. I'm saying we, as in we are part of structure formation, right? You and me. So, and we are part of, obviously stars dying and all that stuff. So we had to make the elements, as in stars had to make the elements, as in galaxies had to form first. So the ordinary matter at that point, again, also coming from Big Bang nucleosynthesis, or in other words, the Big Bang theory, has to be responsible for all of this structure formation, but it doesn't seem like enough matter. Okay? Because only a relatively small amount of normal matter is allowed by primordial nucleosynthesis arguments. This is what I was saying, the hydrogen and the helium. Theorists assume that the universe has to be dominated. So this is one more reasoning, actually, for dark matter. If you have followed us in our cosmology lives, where we talk about the cosmic ingredients, we talk about how much of each of the stuff in the universe there is, we actually know, and this is one more argument for why we need dark matter and why we have dark matter in the universe and why there's actually a lot more dark matter than there is ordinary matter. It's because part of the puzzle actually has to do with this, believe you me. This is what I meant about we want to understand large-scale structure and the complexity of large-scale structure. What makes large-scale structure? I was actually alluding to the fact that dark matter and its role in forming structure in this universe, in forming large-scale structure, is a topic of research. It's a topic of active research. It's a question. So the top 3 questions in the universe right now: number 1, what is dark energy? Number 2, what is dark matter? And number 3, the origin of elements, all of the elements, even the ones that we don't fully understand. We understand many of them, but there are ones that we don't understand as well. These usually lie between molybdenum and barium, but that's a detail. Dark energy, dark matter, obviously, are very big questions. These are unknowns. not enough known, but we know enough to know that there is such a thing. Dark energy has to do with the expansion of the universe. Dark matter is this extra matter, invisible matter that. Oh, thank you so much. Somebody did a super chat. Thank you. Oh my gosh. Hello, Chili Shot. Thank you. Wow, 10 pounds. Goodness gracious me. I'm going to like that and heart that. Thank you so much indeed. Yes, please do make your super chats in pounds because then that'll be more dollars, hopefully. I do like the pound and the euro and all of those types of things. So we talked about the cosmic ingredients, and real quick, we might want to mention them again. The cosmic ingredients, what we have in this universe altogether, are photons, neutrinos, baryons, dark matter, and dark energy. That's it. It's only 5 things. There's only 5 types of things in the universe, if you will. It's pretty simple. It's pretty simple. If you look at cosmology, if you care about cosmology and want to understand things from a cosmological point of view, thank you so much again, Chili Shot. Thank you so much. Really appreciate you. Thank you, Chili. Thank you, thank you, thank you, thank you, thank you. If you think about the cosmological perspective, there's only like 5 different ingredients in this cosmic sauce. And these are photons, that's light. Neutrinos, that's a very light particle, weakly interacting. It's a lepton, cousin of the electron, but no charge. Interacts only weakly, weak nuclear force, and gravitationally. It has a little bit of mass, very small though. So that's neutrinos. Then we have baryons. These are neutrons and protons. That's what we are made of. That's the ordinary matter that we are made of. Then we have dark matter and dark energy. And turns out that most of the universe is actually most of the energy density in the universe actually comes from dark energy first and then dark matter. Most of the matter is actually dark matter and not ordinary matter. If 25% of the energy density is matter, then only 5% of that is ordinary matter, and the 20% of that is dark matter. So it's very it's very it's very mysterious. But the fact is that they were basically kind of thinking about this dark matter even back then in terms of this type of structure formation story, and that is one way of many in which dark matter actually comes up. So if you, again, follow our cosmology lives, you go back and look at those lives, we actually see there are several different types of evidence or need, if you will, for dark matter. It's not just sort of a galactic event, right? Like, for example, we have galactic evidence of dark matter in terms of the orbital velocities of things in our own galaxy, and we know that there has to be this extra matter because things are kind of moving too fast, right? So that's an astronomy or a galactic evidence of dark matter. But there are also cosmological evidences of dark matter, which has to do with more large scale. And one of the big things in which it shows up is actually this large scale structure. And understanding what exact role dark matter may or may not have in creating large scale structure, in driving the shape of large scale structure, that is, the shape of the distribution of the matter in our universe, is actually one of the biggest or interesting questions about dark matter that we must answer and we are researching. Okay? So, simulations. And another thing, too, is remember that Big Bang nucleosynthesis stuff would not have included dark matter, right? The Big Bang nucleosynthesis giving us hydrogen, helium, and a little bit of trace amounts of lithium. Might as well not mention it, kind of lithium. So mainly hydrogen, a little bit of helium, and even littler amounts of lithium came from Big Bang nucleosynthesis. We don't care about dark matter at that point with that particular topic. So it's almost like Big Bang nucleosynthesis gives us some ordinary matter, And then separately, there might have been this extra matter, dark matter. Dark matter, because invisible, right, doesn't interact with photons. And also, we don't know a lot about dark matter. So, I mean, we know some things, but it's still a mystery. It's like this separate thing. It doesn't have to be included in the Big Bang nucleosynthesis story. So the Big Bang is still good. The Big Bang nucleosynthesis is still good. If you say that the extra matter that was needed to form large scale structure is dark matter and it's separate from nucleosynthesis, then you kind of don't have to worry about it as well. Okay? So it's almost like the Big Bang nucleosynthesis people, they can still go to work and be like, you know what, we did a good job. We're good. Dark matter people need to start working harder to understand, well, what is dark matter? What sort of thing really is it? And where is it in this whole picture? We just would, other people are kind of just benefiting from it, if you will, right? So simulations show that the best form of matter for this was the cold dark matter. So I will just mention that there are a few different models or propositions for dark matter. Since we do not know exactly what dark matter is, we do not know what is the particle nature of dark matter, we do not know exactly what dark matter is, if you will, the stuff that makes up dark matter. We don't know exactly what it is. So, since we don't exactly know what dark matter is, there are certain models, if you will, there are certain models of it, there are certain ideas for it, and different people work on these different models. So, one of the models for dark matter is this thing called cold dark matter. So, CDM or cold dark matter is the one that would best describe or best fit with this large scale structure formation. If the dark matter were hot, then it would be moving too quickly to form clumps of the right size. So this is how important these things are, ladies and gents. It's paradox. Which one? So it's extremely important if you're placing on your bets on dark matter to kind of save the day, right? Because there might not have been, it seems like there was not enough matter to form large scale structure because remember those tiny little overdensities or variations or fluctuations in the smooth universe leading to the crazy gravitational instabilities which then caused matter to clump and galaxies to form. There has to be enough of that stuff to be able to make that happen. And the problem is here that there might not have been enough stuff if we're considering only ordinary matter. So dark matter is saving the day here, okay? Dark matter is helping out. But if dark matter is going to help out, it better be the right kind of dark matter, because if it's some other model of dark matter, because people are working on dark matter, it's still a research question. We don't know what it is exactly. And they have some model of dark matter which doesn't fit with this, well, then dark matter will not be able to save the day, right? So it's kind of like it has to be consistent. It has to be consistent. So cold dark matter it's so funny, right? It's so funny. It's like solving this puzzle. You've got this other part of the puzzle which has to do with dark matter, which has to do with this invisible matter, this extra stuff that we need to explain certain things in our own galaxy, for example. So then you come up with models for it because we don't fully understand it, et cetera, et cetera. But dark matter also has a big role in cosmology, in large scale structure. And so hopefully when you come up with the final solution or the final draft, n-1th form or version of dark matter, hopefully it's consistent with these other things too. But sometimes it's not worth thinking about everything, then you get nothing done. So anyway, eventually, after many years of computer time, a picture emerged in which cosmic structure arises in a bottom-up fashion. So general relativity is the theory for gravitation, but it does not necessarily describe dark matter. Because it does not necessarily give us all of the types of matter that there is, okay? So its effect is on gravitation, yeah. But I mean, it's a good question because general relativity is the updated theory for gravitation. But dark matter is not coming as a result of it. Dark matter is coming as a result of observation. We see certain things to have more orbital velocity in our own galaxy than they should otherwise, um, based on how much matter we thought we had. So I talk about the evidence of dark matter, by the way, in a previous live, in a few different lives actually, from my astrophysics point of view type of lives. So there is a few lives in the past where we talked about this, where we discussed the initial dark matter candidates, evidence of dark matter, especially in our own galaxy. So dark matter is a very interesting topic to me because you can sort of approach it both from astronomy, which is more sort of local, as well as from cosmology. So right now we're discussing it from a more of a cosmology perspective, which is really fun. So eventually, after many years of computer time, a picture emerged in which cosmic structure arises in a bottom-up fashion. First, small clumps of dark matter form. Yay! So we are accepting at this point, even though it's a theory, because dark matter is not fully understood. So even though dark matter is not fully understood, we don't know the particle nature of it, etc., etc. Let's say for this discussion, we accept it, as in we accept it because we need it, okay? We're desperate in large scale structure formation. So unless you have a better idea, we're just accepting it as something. And we're progressing, we're proceeding probably with cold dark matter. So actually, I noticed that when you talk to cosmology, what did I say the word right? Cosmologists, cosmology folks, they generally accept cold dark matter. If you were talking to, say, particle physicists' approach of finding dark matter, they might be more open, if you will, to like more types of dark matter or I don't know, something else. But in cosmology, the cold dark matter is very important. It's like they need it to be cold because they need it there, but they don't want it to move too fast because if it moves too fast, then those little variations, those little overdensities will not give us the right clumping, lumping to get the right galaxies and the right distribution of matter. Okay. So it's very important. So let's just say that cold dark matter is pretty much a given at this point from the cosmological point of view. The rotations of things in our galaxy, yes. So we actually saw stuff from the galactic center, stuff that is orbiting our galactic center, the orbital speeds of those increase when we expect them to decrease. Based on gravitation. So it's a gravitational only kind of evidence of dark matter. Okay. So, so yeah, you can definitely look at, you could look up orbital velocity curves for our galaxy to look up the direct evidence for dark matter in our own galaxy. Okay. So we know we have direct evidence of the existence of dark matter, of this existence of like invisible matter that we cannot see with photons, but we know it's there gravitationally. So we have this evidence. But in cosmology, pretty much it's considered a given that we need it to be cold dark matter, because if it's not cold dark matter, then we wouldn't get these fluctuations to lead to galaxies in the proper way that gives us this distribution of matter in the universe or large scale structure. So first, small clumps of dark matter form. These building blocks then coalesce into larger units, which then themselves coalesce and so on. Now remember, this sentence right here is a theory. It's a theoretical sentence. This is what the dark matter theorists are proposing in cosmology to give large scale structure a chance. It will not be proven until we have experimental evidence of dark matter, okay? So RIDS, when something is not proven, I'll let you know. It is a discussion after all, and I'll let you know when something is pending experimental evidence, okay? Dark matter is. But at the same time, there's a lot of evidence for the existence of something extra. Gas, which is made of baryonic material, falls in, stars form, and we have galaxies. So the initial step of the dark matter building blocks is very important. So small clumps of dark matter form. These building blocks then coalesce into larger units, which then themselves coalesce and so on. Eventually, objects the size of galaxies form. Gas, which is made of baryonic matter, falls in, has to fall in a lot, remember. Otherwise, we wouldn't get stars, right? Stars, oh, thank you. If matter didn't just fall, they had to fall a lot in certain spots. Otherwise, we wouldn't get stars, right? So the galaxies continue the hierarchical growth of structure by clustering in chains and sheets. In this picture, structure evolves rapidly with time or equivalently with redshift. Thank you. The idea of cold dark matter has been very successful, but this program is far from complete. So this is what I was saying. Thank you so much for being here. That cold dark matter, even though it is a strong candidate for dark matter and as a thing that's needed, okay, let's just call it what it is they needed dark matter in order for large scale structure formation, which is a cosmological topic. They need it. It's not like they like it, okay? I mean, they like it because hopefully it's a thing. And there's evidence for dark matter in other ways. For example, in our own galaxy, there's a ton of dark matter in our halo. For example, we think that there's a bunch of dark matter in the halos of our galaxy and other galaxies too. So that's sort of an astronomy approach to dark matter. If you were looking for the particle nature of dark matter, for example, we've talked about WIMPs, right? Weakly interacting massive particles. It's a sort of imagined type of particle that might be the particle nature of dark matter. It's heavily inspired by neutrinos, actually. Neutrinos were also considered as a dark matter candidate. That's the particle approach to dark matter. But the cosmological approach to dark matter is the one which gives us the explanation of these things, explanation of cosmic ingredients, explanation of large-scale structure. If you cannot explain large-scale structure with your dark matter candidate, then that would be bad for those cosmological theory people, okay? Because they really depend on it. They want to explain large-scale structure, and they cannot if dark matter fails to do that, okay? So, because just think about it, the ordinary matter according to them, is not enough. So they need more matter of some other kind. So even though it's a good theory, it's a good idea, it's still a topic of research. We still have to go a long way before we can prove these things out. So dark matter, again, anything that I really say about specifics of dark matter, we know that it exists, but if I say something specific about dark matter, chances are that it is to be proved yet. That would be really big headlines once we get closer to understanding what dark matter is, okay? So it is still not known how much dark matter there is, nor what form it takes. Very unfortunate, but also gives us something to do, right? Gives us something to research because we still don't know what it really, really is. The detailed problem of how galaxies form is also unsolved because of the complex hydrodynamical and radiative processes involved with the motion of gas and the formation of stars. So there's also a lot of other complications, such as this hydrodynamical stuff that needs to happen for galaxies to form, radiative processes and whatnot, right? It's not simple. On top of that, you sort of have this dark matter. It's almost like the cosmology way is a little simple because cosmology has to do with the beginning of the universe, the Big Bang, its evolution, as in the evolution of the universe, the early universe, large scale structure, all that, right? So it's almost like you go back to the beginning where there wasn't a lot of stuff. There wasn't a lot of structure or galaxies or anything, and you kind of know, simply put, what there was, and so you know that you have to make this other next thing happen with that. And so it's almost like it's the only, you need dark matter because there's no, like, there's, the ordinary matter is not doing it. So it's almost like cosmology is both really hard and also really simple. It's a sort of this dual thing. So anyway, but now this field is not just about theory and simulations. Breakthroughs in observational technology, such as the Hubble Space Telescope, of course, Hubble is the best, now allow us to see galaxies at high redshift and thus study precisely how their properties and distribution in space has changed with time. So the Hubble, I mean, getting time on the Hubble is pretty hard. You have to have a pretty high priority question. But basically, they've made a lot of progress in observing more and understanding more about the distribution of galaxies, of matter in this universe. With the next generation of huge redshift surveys, so more and more surveys are happening all the time. The dark energy survey is one of them. It's got a little bit of a different goal. It's trying to understand dark energy and the expansion of the universe, but sort of similar. Lots of these surveys are happening now to give us more data, more redshift data, more understanding of the distribution of matter, as well as the expansion of the universe. Both of those are very important. With the next generation of huge redshift surveys, we will have enormously detailed information about the pattern that galaxies trace out in space. This too holds clues as to how much dark matter there is and precisely how galaxies formed. But the final resolution of this problem is likely to come not from observations of the end product of the gravitational instability process, but at its beginning. Interesting. As in, observing the end product of the gravitational instabilities means observing the galaxies, right? Getting the galaxy survey data. But as far as, hi baby, as far as, this is Baji coming here for kisses, as far as understanding how the lumping, the clumping, the overdensity becoming crazy gravitational instability thing happened, which led to the galaxies in the first place, which would have had to have happened with whatever there was, which was the ordinary matter and the dark matter. The answer may just lie in that view of the universe, just because the end product is sort of the effect. We're still kind of wondering about the cause. Um, Antimatter? What do you mean? Proof of any antimatter? What do you mean by what do you mean by that? That there is antimatter? There is antimatter. Just a lot less than matter, but there is antimatter. The Kobe satellite represented an enormous advance in the study of structure formation, but in many ways, this experiment was very limited. Baji, can you not move the phone, please? The most important shortcoming of Kobe was that it lacked the ability to resolve the detailed structure of the ripples in the microwave background. So resolving sort of that detail of finding the variations in the smooth universe, that was a challenge. In fact, Kobe's angular resolution was only about 10 degrees, which is very crude by astronomical standards. The full moon, for example, for comparison, is about a half a degree across. So 10 degrees is not enough resolution. It is in the fine structure of the microwave sky that cosmologists hope to find the answers to many outstanding questions. The ripples in the early universe were produced by a kind of sound wave. So this is very interesting, guys, very interesting. Sometimes these are called acoustic. When the universe was very hot, with a temperature of several thousand degrees, it was ringing with sound waves traveling backwards and forwards. Acoustic waves, kind of. The surface of the sun is at a similar temperature and is vibrating in a similar way. Because of its poor resolution, Kobe was able to detect only those ripples that have a very long wavelength. These represent sound waves of very low pitch. Long wavelength means small frequency or low pitch. The bass notes of creation. The information contained in these waves is important, but not very detailed. Their sound is rather dull. So, I mean, matter shifting around, you could call it sound waves, has sort of an acoustic nature, On the other hand, the universe should also produce sound of higher pitch, and this is much more interesting. Om was the first sound. Yes, there you go. Some spirituality mixed in. Sound waves travel with a particular speed. So look at this. Look at the universe giving us a chance to understand it. Sound waves travel with a particular speed in air. For example, this is around 300 meters per second. So we know the speed of sound in air. Now, this would not be the case in the early universe, but if we're saying that this was sort of like sound waves back then, sort of like acoustic waves back then, well, maybe that could give us some clues now. By the time the microwave background is produced, the universe is about 300,000 years old. We know that. In the time up to then, since the Big Bang, which is presumably, here's Baji, also part of the lesson right now. He also wants to join in. Hi, Baji. He's also reading and understanding everything. By the time the microwave background is produced, the universe is about 300,000 years old. We know that. In the time up to then, since the Big Bang, which is presumably when the sound waves were excited in the first place, they can have traveled only about 300,000 light years. Yes. Oscillations with this wavelength produce a characteristic note, like the fundamental tone of a musical instrument. Wow. It is no coincidence that superclusters of galaxies are roughly of this size. They result from this resounding cosmic fanfare. Unbelievable, unbelievable that there is a structure that follows all of this sound stuff. The characteristic wavelength of the early universe should reveal itself in the pattern of hot and cold spots on the microwave sky. But, because remember, once again, if we're seeing some kind of structure now because of galaxy survey maps, if we're seeing the structure of the distribution of matter now because we see galaxies distributed, because we see observations of galaxies in the sky, that better have something to do with whatever was happening with the cosmic microwave background, because the overdensities in that map, in fact, would have caused these galaxies to form. So what sound, acoustic wave stuff was happening back then, that better be showing up now. So since the characteristic wavelength of the early universe should reveal itself in the pattern of hot and cold spots on the microwave sky. But because the wavelength is quite short, it appears as a much finer scale than can be resolved by Kobe. Oh, Kobe, not finely resolved enough. In fact, the angular size of the spots it produces is around 1 degree. Since Kobe, therefore, there has been a race to develop instruments. So there's a race, a competition to develop instruments capable of detecting not just the fundamental tone of the universe, but also its higher harmonics. So this is what we kind of mean by the higher order perturbations to the smooth universe, the higher harmonics. What about the details? The devil is really in the details here. Those overdensities, what about that, right? By a detailed analysis of the sound of creation, it is hoped to answer many of the major questions facing modern cosmology. The spectrum of sound contains information about how much mass there is, whether there is a cosmological constant, what the Hubble constant is, whether space is curved, and perhaps even whether inflation happened or not. Inflation happened. We know that the universe expands. Two major experiments, the NASA-led MAP mission to be launched in 2001, see this book is kind of old, and the European Space Agency's Planck surveyor to be launched a few years later will make, so the Planck has a map already. You can look at the Planck map. Poor Peter, he's telling us about something in the past, but it's good. He has got a good way of saying these things. Planck surveyor to be launched a few years later will make detailed maps of the pattern of ripples on the sky with very high resolution. So the Planck map is something already you should look it up if you're interested. If the interpretation of these structures is correct, we should have definite answers very soon. So not everything, even with all this happening, we still don't know some things. There's still some mysteries. The sense of anticipation is palpable. In the meantime, there are very strong hints as to how things will pan out. Two important balloon-borne experiments. So I actually didn't know that there were balloon-borne experiments for this, because I worked on a balloon-borne experiment for the discovery of neutrinos, ultra-high energy neutrinos from astrophysical sources, which is also a very similar balloon-borne experiment. But he's mentioning Boomerang, the two balloon-borne experiments, Boomerang and Maxima. Yeah, there will always be mysteries because there's always more questions. But these two balloon-borne experiments have mapped little bits of the sky with only slightly poorer resolution than MAP and Planck will. These experiments have not yielded definitive answers, but they do indicate that the geometry of the universe is flat. Well, we knew that. The space-time, the universe is flat, space-time is flat, we know that. As a shape of the universe, we know that it is flat. The argument is simple. We know the characteristic wavelength of the sounds producing the measured features. We know how far away these waves are observed, about 15 billion light years. We can therefore work out what angle they should occupy on the sky if the universe is flat. If the universe is open, the angle will be smaller than it would be in a flat universe. If it is closed, the angle will be larger. So kind of like this versus this. The results imply flatness. So we have mentioned in some other lives about this cosmological arguments for whether the universe is flat, open, or closed. By the way, you can fit cosmological. You can just assume. You can give each one a try: the flat model, the open model, or the closed model, and just kind of see with newer data which data fits the best. And turns out the flat one is what fits the best. Okay. So the results imply flatness. Got it. Together with the acceleration I talked about in the previous chapter, this measurement also provides strong evidence for a cosmological constant. Of course, this is dark energy now. Dark energy. So in the past, dark energy was just called cosmological constant. Remember, Einstein needed to introduce a cosmological constant as an anti-gravity term in his general relativity equations, because people challenged him with, well, if there's just gravitation in the universe, why doesn't everything just collapse on itself? So he introduced a no joke anti-gravity term, which he called the cosmological constant. But this is before he knew that the universe is not just stable against gravitation, it is in fact expanding. And Hubble actually helped a lot with all of his observations and work to understand the universe and whatnot. But Einstein didn't know about the expansion of the universe back then, over 100 years ago. Since then, we've come a long way. Even now, sometimes dark energy is called cosmological constant. So even the flatness of the universe basically, no, doesn't have to be always constant. No, the universe has evolved, and the cosmological constant, there's actually, it can change. There's a few different parameters that you can actually tune and see how it has changed. The cosmological constant is in fact something that can definitely be tuned and considered more broadly. It doesn't have to be whatever Einstein was doing. Einstein did it, and it's fine. It's fine to consider one type of one sort of avatar of the cosmological constant, if you will, but it can have other forms. Thermal expansion. So space itself is getting stretched out, and there's expansion in the universe. Like 2 points that were closer together back in time are getting farther and farther apart. So that is the expansion of the universe, which we have also confirmed with the actually supernova data. We've mentioned this also in another live where we have evidence. So we talked about the evidence of dark matter here and in other lives, but we also have talked about the evidence of dark energy and collecting a bunch of data to show that literally the distance between 2 points actually increases because of the expansion of the universe at large scales. Okay, so that sort of thing is dark energy, and the cosmological constant is sort of one variation of it. There's more cosmological constants to consider if you want it to be more general. That's a great question. Stretching or being created? Well, definitely stretching because of the expansion. So I don't know. The only way we know of having a flat yet accelerating cosmos is if there is a vacuum energy. So sometimes this dark energy is called vacuum energy of the vacuum, or a sort of a negative energy, which makes things stretch out or expand or get away from each other, versus, for example, gravitation is an attractive force. So it makes things come together, whereas maybe there is some energy in the vacuum. We don't fully get it. We don't fully understand it. It's called dark energy. which causes the opposite, which is the anti-gravity term, which is the expansion of the universe, okay? The picture emerging from structure studies seems to be in line with the other strands I have discussed, but we still don't know how the universe contrived to be the way it is. We still don't know. The answer to this deeper puzzle will rely on deeper understandings of the nature of matter, space, and time. I'll discuss them in the next chapter. So then next, he's going to talk about a theory of everything, which is, of course, the grand, probably, I mean, I have to see it in more detail, but probably he's going to talk about string theory because that is the only candidate which kind of sort of works to unify quantum mechanics and general relativity. I'm looking at it quickly. Yes, he is pretty much talking about that, I think. And oh, actually, this might be kind of cool. We'll talk about this tomorrow. But basically, the theory of everything comes next in this book, which, as far as I understand, in physics is considered to be the grand unification theory candidate, which superstring theory is the grand unification theory candidate that has lasted the test of time, that has stood the test of time. We have talked about other candidates here on the channel as well, but as far as I know, the superstring theory generally is considered the main grand unification theory candidate. So that's probably what he's going to talk about next. But in no way or shape have we answered every question. Indeed, what we're discussing right now is a research topic or topics. Oh, this is pretty good. Actually, I'm looking at his next chapter, and I think we'll go over it as well tomorrow. I think I'm done with this current chapter, but I think we'll actually go over his next chapter because I think he does a really good job of explaining it nicely and simply. But what we discussed today with dark matter and dark energy, I just want to stress that these are research topics, as in we don't fully understand these things, and we have a long way to go before we fully understand or know these things. So definitely stay tuned and do some work yourself, contribute to the field if you want to progress our understanding of dark matter and dark energy. Okay, these are not known fully. So we can talk about these things, we can discuss these things, and we can see what are the things that we do know and ways in which, for example, in cosmology, we need dark matter. Seems like. For example, with large scale structure formation, which is a very important and, of course, relevant topic in cosmology, that is how we all come to be. We would need dark matter, and sounds like we need cold dark matter. But that doesn't mean that we understand cold dark matter and that we have found cold dark matter and that we've experimentally proven cold dark matter. We have to go a long way before that is done, and we are sort of taking the steps towards that, hopefully. So, it is a work in progress, very much a work in progress. And same sort of thing is actually true for dark energy in a sense, because we have come a long way from back when Einstein's days, we didn't know about the expansion of the universe. Indeed, we did not know too much about other galaxies even. We had very little idea because of lack of observational technology that there were so many other galaxies and the universe was so vast. But this whole thing about expansion and us understanding that and looking at supernova data to confirm that and blah 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 blah, dark energy survey. There are surveys happening even now to understand dark energy better. So that is also an open question. Keep in mind, there are some things that we understand, that we know about, and then some things that we don't. Oh, really? Let me write that down. Somebody is giving me homework. Thermonuclear scattering. Oh my gosh. Recite Einstein's equations. It'll help me go to sleep. You should rewind the live if you are joining recently, if you're joining towards the end. Thank you once again. So let me just say, I think I will wrap it up pretty soon here. Let me just thank you once again, everybody, for being here. And thank you so much for the super chat. How very encouraging. How so very encouraging. Gives me motivation that people are enjoying this type of content and there is so much discussion for this type of content. Let me use my other phone to look at the comments because I can't see it very well. I am so glad that people are enjoying cosmology, astronomy, astrophysics, and physics. I love it. I very much enjoy these topics. And so already, so thank you. Thank you for being here and joining for these conversations and these discussions. Very much appreciate you. And thank you so much for the super chat. Was it Chili Shot who did it? How do I look at it again? Because I quickly looked at it earlier. It is such a special occurrence that I want to look at it again. Thanks to you, Baji. Oh, thank you, Chili. Thank you, Eversore. Thank you, Gustavo. Thank you, TX Justin. Thank you, who else? Zebulon. Bye bye. Thank you, Skeletor. Thank you, Carlos. Carlos is here. Eversore. Everybody, thank you so much for being here. I am delighted to see you. But isn't the sound wave stuff so cool? Actually, I have another book. Where is that book? I have a book by Scott Dodelson, Modern Cosmology. That is the first book that I read on the acoustics of the smooth universe and getting like the higher order perturbations as sound waves and whatnot. And so I might bring it back. I might talk about it more from that book too. That would be good. The acoustics are actually quite important to understand. So, because one thing that we haven't talked about too much are the details of these higher order perturbations. So maybe we'll get into that. What do you think? There's Baji back to his tower. Thank you, Jeep. Rids. I saw Rids had many questions. Hopefully you guys helped him out. I couldn't catch everything that he was saying, but hopefully he got tremendous support from the chat in sort of reforming his thoughts here. Okay. I don't see. Rids was trolling. Well, I don't know what he was doing, but it seemed like he had some questions, maybe. Not entirely sure. I'm not entirely sure. And yeah, thank you for the super chat. Rids should have done a super chat. $500. Why not? I think that would have been good. But yeah, unfortunately, it feels like we have been talking for only 5 minutes because it is such an exciting topic indeed. Nice pajamas. I know I'm half in pajamas already. These are indeed my pajamas. I got lazy and the bottoms that I'm wearing are indeed my pajamas. But the top is a real top. But I'll be back tomorrow with the next part of this book, because I think he does a pretty good job actually of explaining the theory. Like his perspective on what the theory of everything is supposed to do would be pretty interesting. And then I think I need to find the acoustic stuff about the smooth universe and the higher order perturbations from the Scott Douglason book. But that book is kind of dense, kind of dense. I don't know who does a very good job. I'll have to find something because I think we are bonding on this part. I'm quite interested. This is actually a very interesting discussion about the, yeah, I think I got to do more with the higher order perturbations and the large scale structure formation. Talk about the possibility of aliens. Huh. Really? Sand on speakers? I don't know. So we can talk about the aliens. One perspective for aliens that I have is really to do with the exoplanet research. You know, a big motivation for the people who are looking for exoplanets is actually aliens, finding other worlds that can support life, in other words. Because aliens, I mean, like, what are aliens, right? I mean, aliens seem to be like this big sci-fi interesting topic, but if you kind of get specific, what we really want is some form of life in other planets, right? In other parts of this universe, probably other planets. Because I mean, stars are not very habitable, right? So I mean, maybe other asteroids, even pieces of rock or some other type of planet. So we have talked about exoplanets on the lives. There were, like I said, there was a time when I was constantly covering all about the planets, like every single day, it was about planets. So I have a playlist on planets, but exoplanets is part of that. And we do this research to find other worlds. One of the motivations is, are there other worlds that are kind of like ours? And could other places support life? So that's really all there is to it. It's not that interesting. I mean, it's interesting, but right now I'm more interested in cosmology. I like the astronomy stuff too. Like I like the planet stuff. I think planets are obviously very, very cool. And we've talked a lot about Mars as well. People like the planet stuff, right? Like the people like Mars and alien discussions and whatnot. But ultimately, finding the exoplanets is also hard. And we keep finding, I believe, more of the Jupiter like and Neptune like exoplanets and not really Earth like ones. So I would say that's my take on aliens. Oh, yeah, yeah, yeah. For aliens to visit us, yeah, that would be quite difficult. Maybe they're not interested in such travel. Oh, did you know that oh yeah, did you know that fast radio bursts were associated with maybe aliens? You should look that up. Hello, Nusrat Ullah Exoja. Hello, Nusrat, how are you? Yeah, so at one point, now I believe that this is not due to aliens, but at this point, it might have been resolved and thought to be something else entirely. I think it's just a phenomenon in this galaxy. So if you've seen my gamma ray burst lives, you know how gamma ray bursts transit events in the sky, obviously transmitting photons in gamma rays, short wavelength photons, very short wavelength light, basically like particles at that point. gamma ray bursts, right? Gamma ray bursts are transient events in the sky that are they occur very far away, gigaparsecs away. So very extragalactic, obviously, very far away. And they're also kind of isotropic, actually. They're a distribution of gamma ray bursts. So interesting, very interesting. I have actually a short book on it, like a review that I wrote myself, and I worked on them and all that stuff, and talked about it on the live. Well, there's this other thing called FRB. So that's GRB, gamma ray burst, GRB, and then there's FRB, fast radio bursts. So for the longest time, I thought that our galaxy was quite boring. Nothing ever happens that's too extraordinary, and all of the interesting stuff, transient stuff, was always extragalactic. But I mean, that's not true. Our galaxy has interesting things too. But um, there was a time several years ago when the fast radio bursts were being discovered in our own galaxy, and they were also associated with aliens, or they thought that it might be aliens or something. So just a tidbit for you guys to look up if you are interested in understanding what that discussion was, or we can talk about it as well at some point. Fast radio bursts. So I would say the fast radio bursts and the exoplanets are pretty much my only perspective or approach. Because for me, like, I don't just want to think about aliens, right? Like, so I'm very like hyper focused on a goal or a topic. So like, if I were to say research aliens, I would have to have an approach. Like, what's the approach? And really, like, what's the way, right? And I would say the ways to research aliens would be, one is exoplanets, and the other thing that was being talked about was the fast radio bursts. Yeah, something like that. Anyways, I gotta go. I need to get some sleep and pick up next time. Pick up with maybe we'll talk about higher order perturbations or the theory of everything tomorrow. So I like Central Asian meals, and you. I'm an experiencer, so I just know. I don't have the luxury of belief. Very nice and good comments and interactions and engagements from everybody. Thank you so much for being here. Good night and see you next time. Okay, bye bye. See you tomorrow. I'll be here tomorrow. Yes, good. Please come tomorrow. Class will resume.